Hello viewers, myself Muniraju Naidu, working as an assistant professor in the Department of Computer Science and Engineering, Institute of Aeronautical Engineering, Hyderabad. In this video, I am going to discuss about memory management and virtual memory in operating system subject. So, what is memory management? What is the necessity of memory management? So, before going to that, this is the overview regarding the memory management. So, what are the various objectives of memory management? What is main memory? What is memory management? Why we need memory management is required in operating systems. So, what is the difference between logical address space and physical address space? And static and dynamic loading, static and dynamic linking, swapping, and we'll see contiguous memory allocations, paging, and structure of a page table. So we know, particularly in operating system, memory management plays an important role, because whatever the process the processor can execute, that particular process must be available in the primary memory. So we know how we need to allocate various processes in the primary memory as well as the secondary memory, and how the processor can capable of executing more number of processes from the primary memory, which deals about the memory management. So here these are the objectives: to provide a detailed description of various ways of organizing memory hardware. How we need to organize a memory hardware like primary memory as well as the secondary memory. Then to discuss various memory management techniques, which includes paging and segmentation. So these are the memory management techniques, paging as well as the segmentation. And to provide a detailed description of Intel Pentium, which supports both pure segmentation and segmentation with paging. So pure segmentation and segmentation with paging. So these are the basic objectives of memory management. So this is the some background related to the memory management. We know what is meant by main memory. Main memory is associated with the processor. So whatever the instructions we are going to execute, that particular instructions are always stored in the main memory. So that's why here the processor executes more number of tasks. So main memory is also known as a random access memory, because that is a volatile memory. So we know what is meant by volatile memory. Whenever any power is lost, then automatically whatever the content which is available in the RAM, that may be lost. Then what is memory management? So particularly in case of multi-programming environment, the operating system which resides in part of the memory and the rest is used by the multiple processors, right? See, let us take, this is my memory, right? So in this particular memory, by default, the operating system occupies some space. So and remaining memory, that is meant for the user processes. So here, whatever the user processes memory, how this particular memory is divided among different processes, that deals about the memory management, which is basically called as a memory management. So now coming to the what is memory management, the task of subdividing the memory among different processes is called memory management. The task of subdividing the different processes is called memory management. So according to the operating system, memory management is a method to manage the operations between primary memory and disk during process execution. According to the operating system, memory management is a method to manage the operations between primary memory and the disk during process execution. So the main aim of memory management is to achieve efficient utilization of memory. That is very important, to achieve efficient utilization of memory. How efficiently we are able to utilize our existing memory. Then coming to the why memory management is required. What is the necessity of memory management? See, first of all, allocate and deallocate memory before and after process execution. So whenever we need to execute some process, right? So for that particular process, let us take, this is my available memory. So here the process P1 is executed, right? So according to the memory, so this particular location is having some starting address as well as the ending address. So allocate and deallocate memory before and after process execution, right? So before execution, this particular process is available in this particular location. After completion of our execution, then automatically we need to deallocate this particular memory. Deallocate this particular memory. So now second one is to keep track of used memory spaces by the various processes. To keep track of used memory space, right? See, this is the, for example, P1 here is allocated, P2 allocated, P3 is allocated, right? So what are the various processes which is used this particular memory space? That particular thing here also we need to maintain. Then third one, to minimize the fragmentation issues. To minimize the fragmentation issues. So later we will discuss about what is meant by fragmentation, because whenever we need to allocate and deallocate space, then automatically there exists some fragmentation issues. So we need to minimize that particular fragmentation issues. Then fourth one, to proper utilization of main memory. Proper utilization of main memory. So whatever the primary memory we are having, that particular primary memory is we need to utilize it properly, right? Then last one, to maintain data integrity while executing of various processes. To maintain the data integrity. So these are the various reasons why memory management is required, particularly in operating system. Then coming to the what are the base and what are the various limit registers. So always the pair of base and limit registers defines the logical address space. So we know basically we have two categories of address spaces: logical address space and physical address space. Logical address space, which is also called as a virtual address space; physical address space, which is also called as a real address space, right? So always the base and limit registers which defines the logical address space. So what does that mean, logical address space? Automatically, whenever any particular process is just open or the particular process is entered into the running state, then automatically the processor creates some logical address space. Processor creates some logical address space. See, for example, this is the memory. So we know within the particular memory, operating system is already occupied, and these are all the various processors, like say P1, P2, P3. Let us take. Right. So these processes are executing. These processes are executing. See, for this particular process, this is the for P2. This is the base. We can call it this. That is the starting address. Right. So what is the length of that particular process? So how much memory it will used? So that is specifies the limit. 120900, this is the base and this is the limit. So 30040 plus 120900. So this is the output. We need to add here. So this is the output. So that means always the logical address space is defined by base and limit registers. Now we can say that the process P2 is having the base address and this is the limit, right? So these two are very important in case of memory management. Then binding of instructions and data to the memory, right? See, particularly whenever any particular process is executed, right? So it gone through the various stages, like we can call it as a compile time, load time and execution time. So what is meant by compile time? If memory location known a priori, that is we can call as a absolute code that may be generated, right? So if memory location known in advance, then absolute code can be generated. So must recompile code if starting location changes. So definitely whenever the starting location of that particular process is changed, then automatically again we need to recompile the code. That is the compile time. Then load time. Load time must generate the relocatable code. Load time must generate the relocatable code if memory location is not known at compile time. If memory location is not known at compile time, then a relocatable code is generated, that is we can call as a load time. Then execution time. So here the execution time in the sense binding delayed until the runtime if the process can be moved during its execution from one memory segment to the another memory segment. Right? So whenever our process may change from one location to the another location, then automatically with the help of some hardware support like base and limit registers. So here we need to cross this particular stage, that is called as a execution time. See, this is the example for multi-step processing of a user program. Multi-step processing of a user program. See here, this is our source program. Initially, the source program is compiled or assembled. That represents here compile time. Compile time. Once the source program is compiled, then automatically it produces the obj file, object module. Like this, a number of source programs are compiled as well as the assembled from the various workstations or various departments. So all other object modules are linked here. That is we can call as a linkage editor. Linkage editor. Now the process starts from this particular linkage editor to the loader, that is represented the load time. Load time. So whatever the object modules, those are linked here with the help of linkage editor, and that represents the load module, and it produces the with the help of the loader. Now the loader, it accepts various system libraries and it transmits the exe file. So this is the execution time or runtime. In memory, binary memory image, right? So that is we can call as a dynamic linking. So these are the various steps regarding whenever we need to process a single program. So first of all, the source program, that is compiled, that we can call as a compile time. Then it produces the object module. Now the object module that produces the loader, right? With the help of the loader, that is we can call as a load time. Finally, execution time or runtime. So what is the difference between logical address and physical address? You know, the concept of logical address space, that is bound to a separate physical address space which is central to the proper memory management. So here the logical address space, that is different to the physical address space, because these two are very important in case of memory management, because you know, whenever the processor, just we need to click on any particular Word document or whatever the application, automatically the processor creates one particular address within that particular primary memory for that particular process. So that is here we can call as a logical address. So the logical address generated by the processor, logical address generated by the processor, which is also called as a virtual address, whereas a physical address, the address seen by the memory unit. So whenever we need to do some task within that particular process, right? So that particular task is required for future references, then automatically we need to store into any particular secondary storage area. Now we need to allocate some space for that particular process. So that describes the physical address. Physical address, the address seen by the memory unit. So both the logical address and physical addresses are the same in compile time as well as the load time address binding schemes. Logical address and physical addresses are the same in both compile time and load time address binding schemes, whereas virtual, that is logical address and physical addresses, differ particularly in execution time address binding scheme. So this represents the logical address. So in depth, what is the physical address? You know, physical address is also known as the real address. Logical address, which is also called as a virtual address, whereas physical address, which is also called as a real address. Now, the set of all physical addresses which are corresponding to the logical addresses is known as a physical address space. The physical address space. Physical address space. Nothing but the set of all physical addresses which are maps to the logical addresses. So definitely this physical address is computed by MMU, Memory Management Unit. Physical address which is computed by the Memory Management Unit. How? The runtime mapping from virtual to the physical addresses is done by that hardware we can call as a Memory Management Unit. Right? So here the physical address always remains constant. Physical address always remains constant. Now coming to the what is meant by static and what is meant by dynamic loading. Static loading and dynamic loading. See, whenever the user wants to execute any particular program, so to load a process into the main memory is done by the loader. So already we discussed from the previous diagram. Whenever to load a process into the main memory is done by the loader. So there are two types of loading. One is static loading, another one is dynamic loading. So static loading, loading the entire program into a fixed address. Loading the entire program into a fixed address, it requires more memory space because we don't know exactly what is the size of that particular program. Then dynamic loading. So the entire program and all the associated data of that particular process must be in the physical memory for the process to execute. So here what happens in case of dynamic loading, the size of process which is limited to the size of physical memory. Right? See, to gain a proper memory utilization, always dynamic loading is used when compared to the static loading. Then in case of dynamic loading, a routine is not loaded until it is called. So whenever there is a purpose for a routine, then only we need to call that particular routine, and that particular routine need to occupy the space. All routines are residing on the disk in a relocatable load format. So what is the advantage of this particular dynamic loading when compared to the static loading is that unused routines are never loaded. Unused routines are never loaded. So this loading is useful whenever large amount of code is need to be handled efficiently. Whenever any particular program which is divided into the various sub-modules, right? What happened? Individually each and every module is executed. But whenever we need to combine all the modules, then definitely we can go for this dynamic loading. See, this is the relationship between dynamic relocation using a relocation register. Right? So we know initially the processor which generates the logical address. Processor which generates the logical address. So this is the logical address. And this is the memory management unit. So within that particular memory management unit, this is the relocation register 14000. Now this particular relocation register is combined with the logical address and it produces the physical address 14000 plus 346 14346. So this particular 14346 in case of memory, it occupies somewhere 346 like this. So this is the dynamic relocation using a relocation register. Then coming to the next concept, swapping. Swapping. So what is meant by swapping? What is the necessity of swapping? What is the purpose of swapping, particularly in memory management? Right? See, swapping is a process of swap a process temporarily. Already you are very familiar about the swapping. Swapping of two numbers using the third variable, or swapping of two numbers without using the third variable. Right? So what is the necessity of swapping? See, swapping is a process of swap a process temporarily into the secondary memory from the primary memory. Right? So why we need to swap any particular tasks or programs from secondary memory to the primary memory? Right? Because always the processor can accept the process for execution purpose only from the primary memory. So always we need to maintain primary memory as free as possible. So this is very fast when compared to the secondary memory. So here swapping allows more number of processes to be run and can be fit into the memory at one time. So the swapping allows us more number of processes to be run. So for example, whenever I need to execute one particular application, already my processor which is capable of executing 10 more applications. Right? So what happens? I need to check that whether which application I may not be used for the longest period of time, or else by default the operating system chooses whatever the application that depends upon the here the priority scheduling will play an important role. right? So which process is having the highest priority? That particular process resides in the primary memory. Which process is having the lowest priority? Then automatically the processor swap out that particular process to the backing store, and whatever the process we need to execute, so that particular process is swapping from the backing store to the primary memory. So here we can call it as a concept called as a rollout and roll in. So the swapping allows more processes to be run and can be fit into the main memory at one time. So the main part of swapping is transfer time and the total time. Transfer time and total time, which is directly proportional to the amount of memory swapped. So how much amount of memory we are going to swap, like 100 KB or 1 GB. Right? Again, what type of data you are going to swap? Whether you are to trying to swap documents or PPTs or some video files or images, something. So here the swapping is depends on transfer time and the total time, which is directly proportional to the amount of memory swapped. See, swapping is also known as rollout and roll in, because if any higher priority process arrives, then the particular process requires some services, then automatically the memory manager can swap out the lower priority process and execute the highest priority process. So definitely here the memory manager can swap out the lower priority process and swap in the highest priority process from the backing store. After completion of highest priority process work, then automatically what happens? The lower priority process swapped back in memory and continue to the execution process. So this is the necessity of swapping in memory management, right? So if less number of applications are running by my processor, then no need to swap anything, right? So what happens, whenever I need to execute more number of applications, still some more processes are ready to execute, but there is no space in the primary memory, then depends upon the priority, whatever the lower priority process is there, the particular lower priority process swap out from the primary memory to the secondary memory temporarily, and whatever the process which is waiting at the secondary storage for execution purpose, so that particular process swap into the primary memory for execution. After completion of my work, whatever the lower priority swapped back in the memory, and that particular process is go for the execution process. See, this is the schematic view of swapping. Schematic view of swap, whatever the concept till now we discuss, right? How the swapping will works. See here, this is the primary memory. We know primary memory which occupies some space to operating system. So these are the user space. So in case of this particular user space which is allocated to the number of processes. So this is the backing store. So what happens here? There is no space. Then the memory manager swap out the process which is having the lowest priority. See, that's why here we need to mention that swap out. See, for example, here the process P1. So the process P1 is swap out from primary memory to the backing store, and whatever the process which is waiting at the backing store for execution purpose, now the particular process is swap in. So this is the process. This is the process P2 is newly arrived process. So now the primary memory which executes this particular process. So this is the schematic view of swapping. Then next one is a contiguous allocation. So what is the necessity of contiguous allocation? How the primary memory is divided into the various partitions, and what is the hardware support for this particular contiguous memory allocation, right? So depends upon that we have fixed partition allocation and dynamic storage allocation problem is there. So that represents this contiguous memory allocation. So contiguous allocation, yeah, we will discuss later this contiguous allocation.
Like, share and subscribe. Hit the bell icon for more updates.